Hello everyone, this is Jack from the PyTorch XLA team. So today I want to cover another quick topic, which is how to use the PyTorch XLA to do the inference. So today's agenda item, first I'm going to talk about how to do it and what to check, and very quickly we'll just look at a Colab example. So the inferencing using the PyTorch XLA is actually very similar to the PyTorch if you want to inference on CUDA. So first you need to move both your model parameter, like an all of the input, to the X-ray device. And then for the further optimization, you usually want to use the torch.compile. So I will show you in a minute in the Colab. Then what to check is also very simple. For the most part, you only need to check whether your model generates a single execution per step. So as usual, I will put a link to the Colab and a slide on the video description. So first thing you want to do is you want to change the runtime type to the TPU v2. So you are using TPU. Let's restart the runtime. Okay. Let's do the import. So I also set this ptxray_debug flag. So if you don't know what it is, check my previous video. So it go into depths of what this debugging flag will output. So it's in Colab. For some reason, like the C error doesn't directly get outputted, so I have to specify a file that you can actually check on the terminal, like under temp, after we actually start running the program. So let's see. So as we said, the first step is actually move your model. In this case, let's start with like the dummy example, which is just a linear layer. You need to move both your model and the input to the device. And that is actually it for you to do a very dummy, non-efficient inference. Okay, it's taking a while. So what is mat? So we actually import mat in here is torchxplay.debug.matrix. So we will talk about why we want to do it here. So let's define your inference, the model here, the inference code here. It's actually very simple. So pretty much just a torch.nograd, and then you run your model with the input. And then for now, let's just add a mark step. You don't need it anymore. You don't need it in the future if you use torch.compile. Which, because in here, if you watch my previous video, we are only tracing the linear layer, and then here is where the execution actually happens, and then we just return the result. So yeah, so if you just run it, because both the input and the linear parameters on the device, the X-ray device, the output tensor is also on the X-ray device. So that's actually it. Like that is the minimum thing you need to do to inference PyTorch X-ray using the PyTorch X-ray. But it's generally there are a couple things you want to check before you call it done. So the first thing you want to check is like how many execution you have like per model. So in here it's very simple. We just executing a single linear model. So if you print the mat.show matrix report, it's going to tell you that we compile once, which takes 324 milliseconds, and we execute once, which only takes 7 milliseconds. It's okay because like it's just a linear model. It's just pretty much execute instantly. And like if you only execute once, compile time is almost always greater than the execute time, and that's okay. And we transfer from device once. I think that's probably the parameter. So let's get. So this is good. So this means this is the first thing, which is there is one execution time here per step, which means like you execute your linear your model once. So this is a good thing. This means compiler and PyTorch X-ray was able to capture like all of your model into a single execution, and the X-ray compiler were able to optimize it. In this case, you will actually get pretty good performance. And in the case where like you actually see multiple executions, that's usually like two things. The one common issue is like the op fallback. So let's take an example here. So we first want to clear off the previous matrix so like we can start seeing the matrix for this portion of the code. So let's say like for example, torch.non-zero is an op that PyTorch XP does not support. When that is the case, like the input tensor will be moved from the device back to the CPU, and then the execution will happen on the CPU, and then it will be moved back to the X-ray device. in that case, you can tell that it's not very efficient. And how can you check whether that's a case happen to your model? Well, you just execute your model once, and then you do the sensing mark step, and then you print a matrix. Then you will see something like here, like counter, like A10 : non-zero. Every time you see the counter starting with A10, that means like that's an op that's not supported on PyTorch X-Ray. In that case, you are encouraged to open a PyTorch X-Ray GitHub issue, and then we will try to lower it. Non-zero is kind of special case because it's a dynamic shape. You will introduce dynamic shape. Dynamic shape means for example, for non-zero, the input shape is constant, but the output shape is actually depends on the runtime value. In that case, compiler cannot predetermine the output shape of the tensor. That is usually a bad behavior for the PyTorch X-Ray. Which is actually a great transition to our second topic, which is like after you check let's no fallback, if you still see like let's more than one execution per step, another thing you want to check is dynamic shape. So how do you check dynamic shape? The one general thing to do is that, for example, instead of execute your model once, you want to execute your model multiple times. Let's try here. Did we clear? Okay, we clear. So in this case, we execute the linear, which like, if you remember single step linear, just call linear and then return 10 times. Then you see we compile once, which is expected, right? Because like it's a single model. And the remaining 9 times the compile is cache, and then we execute 10 times. So you see here, we call the single step linear 10 times and execute 10 is 10. So that is good. So what is not good? What is not good is like, for example, you execute this model 10 times and you see the compile times 10. So that means for every single time you run it, you will compile, and compile is generally slow. So your ideal situation is compile once and execute many times. Oh well, ideal is once, but it can be fine if you compile 4 or 5 times. But as long as your compile time does not grow with your like the model execution time, it's actually acceptable. So if your model is compiling for every execution, or you is compiling multiple steps, the one way, and like the first thing you want to check is whether the input shape is constant. For example, here, if you're changing the input shape here, like instead of 1 by 10, you change 3 by 10, 4 by 10, it's expected way to recompile. So the first thing you want to do is you make sure the input shape to your model is static. But if you still see the multiple compilation for the single function, that pretty much means like there will be some dynamism in your model. In that case, you want to follow the instruction in our troubleshooting to actually dump the HLO or the IR graph. And then from that graph, it actually has all of the shape attached to it. You can just do a diff on the compilation on different steps, then you probably will find out like why recompilation happens. It usually happens like in one of the steps, the intermediate shape is different, and then you can go back and see like why that's the case. All right, so if all of them is checked, which means like that is actually one execution every time you call your function, that's good. And then lastly, to optimize like your inference is to use the torch.compile. So if you're not familiar with torch.compile, you can search it. Like it's not something that's specific to PyTorch X-Ray. Like it's actually a compiler entry point like for the PyTorch itself, starting PyTorch 2.0. PyTorch X-Ray implement a backend called OpenX-Ray. So you want to torch.compile your model with the pass backend to equal to OpenX-Ray, and then you got a function back, which theoretically it should perform the same thing but much faster. So in that case, you run the same code. Just instead of run the linear directly, you run a compile linear. And then you should see the same thing, like you should still execute one time. And you even notice like the execute time does not improve. So that's confusing. Like if execute time doesn't improve, why would you need a torch.compile? Well, this is because that for the case of the PyTorch X-Ray, the torch.compile does not optimizing the device execution time. It actually optimizes the CPU side overhead. So this means that without torch.compile, every time you run your like model inference code, we will execute all of the Python PyTorch code, and then we will execute. But with touch.compile, it pretty much cache like all of the Python compile. It directly execute the device program, which is actually a very significant improvement for the inference because the execution inference is usually a lot faster. For training, it's like less of an issue because training execution time is actually a lot longer than like the CPU overhead, and the CPU overhead can usually be overlapped with the device execution. But for inference, like we almost always recommend to use touch.compile. Touch.compile doesn't always work. Sometimes it will throw some error, or sometimes it's actually going to introduce some graph break, which is why you, like after you use touch.compile, you still want to monitor this execute time. So that is it for the linear model. You can actually apply the same knowledge to like whatever model you have, but for the sake of this collab, let's just use the ResNet 18. So you will see it's actually very similar. Like you initialize like the ResNet 18, you move it to a device. Like you compile the model, which is an 18, we call it compile model. You initialize a single image input, which is a batch channel and 2D, and you move it to a device, which is everything we just did with linear. And then let us try to run this model. So it's actually the one fun fact is like when you call touch.compile, it actually does not compile the model. It compiles the model the first time you execute it, which is why like you see the model is kind of tying here for a while. So we want to execute this compile model 10 times. Well, you see this compile time execute time is kind of off, right? Like we expect compile 1 time execute like 10 times, but it's actually compile 2 times execute 11 times. That's actually expected because during the touch.compile we actually need to execute something for the cleanup. So, but if you run it again, you see like we don't recompile because we clear. We only execute 10 times. You can keep trying, it's always the same thing. So yeah, like that's it. That's the basic example for you to actually run your inference. If you want to follow optimizing your model, like you can check my the first video, in which it will cover how to actually cover how to look at a profile, collect a profile, and that might be your second step. So that is everything I want to talk about today. So thanks for watching. See you next time.